So here we have few problems from heterocycle chemistry. So this is the first problem. So here we have Pyrrole. Pyrrole. Here we have taken a base. Okay, and this base abstract this hydrogen. Okay, so now it will become a N minus, and this potassium goes and attacks to this N. So now the product of A is, it will be N minus, and this will be a K plus. So in the next step we have a methyl iodide. So methyl iodide, we know that CH3 plus and I minus. So this methyl plus goes attacks to this N minus, and this will then it will get converted to NCH3. Okay, so what will happens? So then in the next step we have a heating. Okay, so when we heat this one, this product, it rearranges itself, so we'll get this compound 2-methyl pyrrole. Okay, so just remember this. So up to this it's okay. So here methyl group goes and attacks to the nitrogen. So when we are heating it at 200 degrees centigrade, so this product rearranges into this product. Okay, and next we have this compound. Here we have acyl chloride. This is a Pyrrole-Kapff acylation reaction. So the A product is this one, COR. And next we have a acetic anhydride. So here also acyl group comes. So where it comes? So when we are talking about a pyrrole, here 1, 2, 3, 4, 5. So the electrophile goes to second position or fifth position. Okay, this is a general. So when it goes to second position, when it goes to the fifth position, if no substituent at all, then electrophile goes to second position. Okay, if second position is occupied, let's imagine that this is occupied, now electrophile goes to fifth position, and if both are occupied, then only electrophile goes to third and fourth place. So here the second position is already occupied. Now the electrophile has to goes to fifth position, that's here, and this here COR. So this is the product. This is A is the this is A product, and this two acyl group is a B product. Okay, and then so here we have taken AlCl3, but here if you see this reaction, so this one, so here we have a base first. So in the presence of base abstract this hydrogen, then it will become a negative charge. Now this carbonyl carbon goes and attacks to this pyrrole, so the product will be COCH3. N-acyl pyrrole is a product. So when we don't have base, so we will be having a electrophilic substitution reaction. If we have a base, so you will be the acyl group will be coming to this nitrogen. Okay, and we'll see this one. This is very, very important. So here we have to talk about this substituent here. Okay, so when we have a NH, in this case the electrophile goes to second position in general. If imagine that this group is some methyl group, no doubt there also electrophile goes to here. So when we have some bulky group, imagine that this is the group we have at this position. So when we have a bulky group, this electrophile cannot approach this position. Rather than this position, it goes to the third position. So this we have to remember. Okay, when we have a bulky group at nitrogen, the electrophile goes to third position. So in case of methyl, second position only the major product, but other things like butyl, N-butyl, then profile groups, for them we will get a C3 attack as major. And here we have SO2 and SO2 pH, N is like this, SO2 pH. First we'll see this one, HNO3 acetic anhydride. So here we have three, you have three, means like first one is, so in this case, since this is a bulky group, so as I said that if nitrogen attached to the bulky group, the electrophile goes to C3 position, so NO2 goes to this position. So the product what we will get here is, so this is the product, here we'll get NO2. Okay, and then we also have here Lewis acids. Okay, BF3OET twice and AlCl3. So in these two cases, what will happens, we'll see now. So when we have a BF3 case, in that case we'll get a 2-nitro product. When we have a AlCl3, in that case we will get a sorry, this is acylation, not nitration, COPH, and here COPH. Okay, so only in case of BF3 we are getting a 2 acyl product is major, whereas in case of AlCl3 we are getting a 3 product. So this is because of the Lewis acidity. So if you see the BF3 and AlCl3, BF3 is a strong Lewis acid compared to AlCl3. So because of that, as we know that third position and second position, which is having more electron density, second position is having more electron density. Since BF3 is strong Lewis acid compared to AlCl3, so this will direct the electrophile to the C2 position. So this is very, very important. You have to remember this one. Okay. If no BF3, then third position electrophile is major. If BF3 is there, it has to go to the second position. And then here we have this formylation reaction. This is a Vilsmeier-Haack reaction. So here also, as I said, that the product, it can be either C2 or C3 or C2 substituent. So this mainly depends upon this R group. If R group is ethyl, then so C2 is the at C2 this one, this is the product. C2 means NR, this is the product. C3 means this is the product. If R group is ethyl group, this is A and B. So A is major, B is minor. If this is the tertiary butyl group, B is major and A is minor. So just remember, if R group is either methyl, ethyl, in these two cases C2 is major. Even if it is a profile also, isoprofile, here also C2 is major, but C2 and C3 almost equal. This is 1.9 and this is 1, so almost coming very close. But if you want to see the proper differentiation, so that we can see only for the tertiary butyl group. When you have a tertiary butyl group, in that case the C3 substitution is major compared to C2 substitution. At any bulky groups you can see this also possible, IPR. In this case there is no doubt of C2, only C3 is possible because this bulky group is there. Okay, even if you see this compound NSO CF3, so here also you will be having a 3 substituted product is a major product. So then we'll go next problem. So here we have this problem, this is over. So here we have esters, 2 esters and 2 methyl groups. In one case we have a acid hydrolysis of esters, in other case we have a base hydrolysis of ester. So we know that ester hydrolysis forms carboxylic acids. Now, which ester involves in the reaction in presence of H2SO4, in presence of NaOH is very very important. So it's just apply simple concept here. So this is the base. Base means what? We can consider as a nucleophile. So this goes and hydrolyze the ester group which is having a less electron density. So see, this ester group is flanked between two methyl groups, so this is having more electron density. So the acid goes and hydrolyze this one, and base will hydrolyze this one. Okay, in the presence of acid hydrolysis, the product is, this is the product in the presence of acid, and in the presence of base hydrolysis of ester, this is the product. Next, so this also this question also important. Here we have furan in the presence of Br2 and methanol. Okay, so the first step is the Br, this will be like this. This bond goes on to Br, and this double bond takes this Br, and this lone pair goes here, and this comes here. This is the Br. Okay, so now we have a, in the reaction mixture we have methanol, OMe. So here we have positive charge, this bonds comes here, this comes here. Now this will be O, Br, OMe, and here we have a double bond here. Now in the second step, this lone pair goes like this, and this bromine leaves from here. So Me, and here we have a positive charge. So in order to neutralize that positive charge, this bond comes here, and this lone pair attacks to this alpha carbon. So the final product is OMe. So very very important, this question, sorry, the final product is this one, only one double bond. So this is very very important. So here the product is OMe, and here also OMe. And then this is a very simple reaction. We have a this is a Riemann-Tamer reaction. So we'll get a alpha position, CHO, then we have a Wittig reaction, and next we have a here Wittig reaction. So since this is a stable halide, we will get a E product as a major, then protonation step. And this is very important. Here we have, in the first step we have N beta lithium, negative charge comes, and then we have a carbon. So the carboxylic acid forms here in the first step. Next reaction with Br2. So as I said that in case of pyrrole, if C2 position is occupied, next substituent goes to the C5 position. So here C2 is occupied, and it goes Br2 goes to, bromine goes to this position. So the product here we'll get is COOH, and this is the Br. So this is the A, and in the B we are just heating it. So when we have carboxylic acids, if we heat it, then the elimination of carbon dioxide takes place. The final product is, this is the final product. So this is the B here. And then we are treating a furan with PbOAc twice. So here byproduct is PbOAc twice. From PbOAc4, the byproduct is this one. That means two acetate groups are reacting here. So those two ester groups, as I said, that it goes to C2 position and C5 position. Okay, then we have this one, this compound, and here Cn minus is there. Okay, here just nucleophilic substitution takes place. Here we have so this is the reactant CH2Cl. In the presence of NaCN, the nucleophile substitution takes place here. So this is the product. Okay, and next we have a here protonation. So we know that nitrile, if you do the acid hydrolysis, we will get a carboxylic acids. So H plus H2O, this gets converts into carboxylic acids. Okay, and then we have, this is the A product, and then we have SOCl2 and again furan AlCl3. So SOCl2 means this will gets converts into COCl, right? In the presence of SOCl2, this will, and then here we have furan and AlCl3. So now this can act as electrophile. Okay, and this attacks to this alpha position. So now we'll get a COCH2 CH2 COCH2, this product. Okay, and then we have a zinc HG. This is a reducing agent. It gets it converts carbonyl compounds into CH2, and this carbonyl compound gets converts into CH2, and the product what we'll get is this product will get. And then here we have methyl lithium and Li. So this is generally here we have the nucleophilic center is a carbon. This methyl goes and binds to this carbon, and the product here will get is CH3. Okay, in the next step we have H plus that attacks to this oxygen. Okay, now this gets opening, ring gets opening here, and the O minus attacks to this carbon, and now the product what we'll get here is, this is the OH, this is the OH, this. So this is the enol form, it gets converts into keto form in order to get a stabilize. Okay, now if you see the reactive preparation methods of pyrrole and furan, okay, these two are very very important. So these two comes under preparation methods of pyrrole. So what this 1,4-dicarboxylic compound, if we treat with the ammonia, the elimination of water takes place. Elimination of water takes place, and it leads to form a pyrrole here, N-methyl substituted, sorry, methyl 2,5-methyl disubstituted pyrrole will get. And similarly here also will get a furan. So these are the preparative methods of pyrrole and furan. So here the B is this product and C is this product. And then we have a this one, this we'll see later. Before that we'll go here. So these three reactions are very very important. Okay, because like here the substituent is present at a C3 position. So when the substituent is present at C3 position, in that case, okay, first we will see this, then we will go here. So this is the simply 2+2 cycloaddition reaction. O, R and R. So here the attack will be this side. So always remember here there are two kinds of attacks possible here. So this attack also possible. Okay, so if this attack takes place, the product what we'll get here is this one, and if this attack takes place, so this is the product. But which one is the major here? So as we know that in this case this oxygen is a electron withdrawing group, and this has to attack where more electron density is present. So at C2 position we have a more electron density, so because of that oxygen attacks to the C2 position. And now if we do the protonation of this compound in order to opening the ring cycle, because of angle strain this is not stable actually. So the lone pair attacks this H plus, then we have like this. Okay, and now this bond goes on to this, and then this bond goes on to the oxygen. This will be like this, sorry, here plus this is R OH. So now in order like this hydrogen goes here, this double bond comes on to the oxygen. So here I will explain from here. So here the proton is attacking this hydrogen, this is OH plus R group and R group. Okay, so now this lone pair goes on to the oxygen, and this goes on to this oxygen. Now we have a plus charge here, R and OH, and next this hydrogen forms a bonds here, and this double bond comes on to the oxygen. So we'll have this kind of compound here. So this is the product we'll get in this reaction. Now when we have this kind of compounds, substituents are present, so what you need to remember is when electron releasing groups are present, in those cases ortho and para product is major. When electron withdrawing groups are present, in those cases meta product is major. Okay, so here we have a carboxylic acid, and in this case, sorry, so when electron withdrawing group is present at a C2 position, in that case the when we have a electron releasing group, in those cases ortho and para product will be major. When we have electron withdrawing group, in that cases meta product is major. Okay, so here we have electron withdrawing group carboxylic acid, and bromine goes to the meta position, ortho meta. So here the product is, this is the product, and then here we have a bromine. So mostly in this case ortho meta, so here no para, only ortho is there. Ortho also C2 is ortho, and this C4 also ortho, but normally electrophilic reaction takes place where more electron density is there, right? So since this position is electron rich and also it's close to bromine, so bromine provides extra electron density, so because of that reason the electrophile goes to the second position, and here the electrophile goes to meta position, because NO2 is electron withdrawing group, it goes to the meta position. So this is the major product, and also minor product will be this is the minor product. but the major product is a meta substituted compound. And when we have a methyl group, in that case here ortho, meta, para. So here two products comes. The major product will be the para one, NO2, and the minor product will be the ortho one. Okay, and then we have a here we know that if sulfur gets oxidized, we'll get a sulfur oxides like this. So this is A, and the AB product will be this is the B product. So these are the some problems I have collected. So still some more problems are there. I will be I will be making another video. If you like my video, please subscribe to my channel and please forward to your friends. Thank you.